All right, in section 3 we talked about maximizing and minimizing problems and how they can both be set up in a data box in kind of a complementary way. Let's go back and take a look to review. Now here's a data box for a maximizing problem. The function to be maximized is on the bottom. This is profit. The constraints are expressed on in the rows. This units assignment gives a consistent units. Now notice that the column units are in the denominator and the numerator units are in the rows. But in order to get the units of any item in this box, you just take this divided by this, man hours per auto, and so on. And then the total profit will be this value here, and this is what you want to maximize. So you read the equations across, and the variables correspond to the columns. And I mentioned that the variables, the equations really correspond to this matrix multiplied on the right by a column vector of variables. All right, so that's for maximizing problem. For minimizing problem, we have another data box down here. In this case, you were trying to minimize cost, and these are cost per day, and this is the total cost that you want to minimize. The unit of this total cost is dollars per week. So you notice that the units on the rows are in the denominator, and the units in the columns are in the numerator. And a lot of what I just said about maximum holds, except this time you're reading the equations down, and the variables correspond to rows. So, in fact, the two constraint equations correspond to a row vector of two variables multiplying this 2 by 2 matrix here. Now, notice that if I just gave you the box with the numbers, you couldn't tell whether it was a maximization or a minimization problem. It looks exactly the same. So, in some sense, you might think that the solutions of these two problems are related. And in fact, they are. We'll find that to every maximization problem, there's a minimization problem, and vice versa. All right, so that's what this section that we're into, section 4, is going to be talking about. Okay, so here's a pair of problems that are paired together. Your maximum problem, minimum problem. Here we're maximizing Cx. Remember, these are vectors. C is a row vector, X is a column vector, subject to Ax less than or equal to B. X is on the right-hand side. A is the matrix. The inequality is a less than or equal to, and all of the x's are positive, non-negative. And you have a minimizing equation where you're minimizing VB. B is a vector, B is a column vector, V is a row vector of variables. In this case, the variables are on the left, and the constant vector is on the right. Now here you have, the constraints are VA greater than or equal to C. Again, the variable is on the left, and the matrix is on the right. Here the constraint is greater than or equal to, not less than or equal to. And we still require the variables to be non-negative. Okay, and these two problems are called dual linear programming problems. And if you have a maximization problem, you can find a dual minimization problem. And if you have a minimization problem, you can find a dual maximization problem. So here we go into detail about how to set up the data box for a maximization problem. The variables go across, the constraint limitations go down, and the profit function goes across on the bottom. And then these coefficients are filled in from the information supplied in the problem. This is the matrix A that is specified up here. All right. So that's where A, B, and C go in the data box if you had a problem in this form. Now, for a minimization problem, you do it differently, and actually the box looks the same, but the significance of B's and the C's are different. B here is now the cost function, and the C's are the constraints. Okay, so cost function goes here, constraints go here. So there's a very slight difference between these two boxes, this box for maximization and this box for minimization. So what's the difference? The difference is only where you put the variables. Here the variables go across, here the variables go down. And that's reflected in this statement here that the variables here go on the right, variables here go on the left. Now, one thing that may be uncomfortable about these problems is that they deal with inequalities. And we're used to dealing with equalities. Up through high school, most of college, we've dealt with equalities. So what we're going to do is actually change these problems into equalities, and we'll see how that works. Notice that if ax is less than or equal to b, that means that ax minus b is less than or equal to 0. So ax minus b is a negative number. Right? Similarly, if bx is greater than or equal to c, then bx minus c is a positive number. And here we have constraints on x and b. X is positive, b is positive. So we can add another constraint and change these inequalities into equalities as follows. For instance, this example. If I have an inequality, which is a constraint inequality, minus u plus 2v less than or equal to 5, I can write that as minus u plus 2v plus w equals 5, where w must be positive. Right? In order to make this side equal to this side, I have to add a positive number. And we still have an equation in positive variables. All of the conditions on the variables say that the variable has to be positive. Okay. So this introduction of this new variable from the inequality is called a slack variable. And the fact that I can add a non-negative variable here to the left-hand side to get equality is expressed right here. Each row of this matrix equation is a constraint like up here. Oops, where's my mouse? Like up here. And by adding a non-negative number to each constraint, I can make an equality. This y is a column vector that's added to this ax here. Now, the other thing that's new here is this cx equals f. F is just a name or label for the value of cx. We can do a similar thing with the minimization problem. Remember, the minimization problem has this restriction that, go back up here, VA is greater than or equal to C. So in other words, to make these two sides equal, I would have to subtract a positive number from the left-hand side in order to make these two equal. That's the same thing as adding a positive number to the right-hand side. So we're going to add a vector of positive numbers to the right-hand side, or subtract from the left-hand side. I don't remember which. This is maximum. So here you are. You're subtracting a vector of positive values from the left-hand side in order to make this an equality. So that brings us to this box here. All right, so what does this box mean? We can read this box in two ways. We can read it as a maximization problem or as a minimization problem. In the maximization problem, the x's are the variables. Okay, so if we read the x's variable, as we read across, we multiply these variables by each one of these rows. So we have x1 a11 plus x2 a12 plus dot 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 plus xn a1n minus b1 equals minus y1. What does that express? That expresses the first equation in this vector matrix equation. Right? It's the first row of A times the column vector x minus the first entry in B is equal to the first entry in Y with a negative sign. All right, so if I wrote these out equation by equation, I would get these equations going across like this. Now, the maximization part hasn't changed. I'm taking x1 times c1 plus x2 times c2, etc. I'm just saying the result is equal to f. F is my name for the result. Right? So if that's what I get if I read this box as a maximization problem. If I read it as a minimization problem, I read down. I read this constraint down, v1 a11 plus v2 a21 plus etc. minus C1 equals U1. That expresses this equation here. And here you're taking the first, the result here is actually a row vector because you're multiplying a row vector times a matrix. And you can verify if you take this equation row by row, column by column, you will get these equations one by one. And then G is the name for V times B. The other innovation here is that you don't put F and G in this box. G is the sum of V1, B1 plus V2, B2, dot, 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 plus Vn, Bn. Sorry, where's my mouse? It's getting stuck here. It's V1 times B1 plus B2 times B2, etc. All right, and the F is C1 x1 plus C2 x2 dot, 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 plus Cn xn. Now, I encourage you to read through this example down here and see how this is working in a simpler example. It does take a little bit to get used to, and you will have some practice in writing these two equations, but it's good to be able to see the same thing from two different perspectives. All right, we have another example down here. And now we get to something that's relates the two pictures together. Remember, G was the solution to the minimization problem. F was the solution to the maximization problem. So there's a relation between the solutions of these two problems. G minus F equals Vy plus Ux. So let's see how this works out in step by step. So first of all, if I take G minus F, what's the definition of G? Well, G was the minimized quantity. The minimized quantity, if you go way back up here, the minimized quantity was VB. F is the maximized quantity. You go way back up here, that's Cx. So I can replace G with VB and F with Cx. Right. So let's go down there and see that. Sorry, I'm not sure what this is doing. Okay, keep going. Keep going. Okay, VB minus Cx. All right, so how do you get from this stage to this stage? Well, what you do is you replace the B and the C with their expressions in the constraint equations. This follows, what this is implying is B equals AX plus Y, and that comes from up here. B equals AX plus Y, or you can do it right here. B equals AX plus Y. Similarly, C equals VA minus U. All right, so that's how you get this substitution here. So this is all about substitution. You just need to substitute the right things in. So if I substitute these things in, lo and behold, something happens. Here I get VAX plus VY. All right, so you can distribute just like you distribute with numbers. Here I get minus VAX minus UX. All right, so the VAX's cancel, and you're left with VY plus UX. All right, so you might think this is just playing with numbers, but this relation is going to help us find some very deep relationships between the solutions of the maximization and minimization problems. And that brings us down here. All right, now, we don't just want any X, Y, and F in our solution to the data box. We want the best one. We want to find F that is maximized. And similarly for the minimization problem, you want to find G that is minimized. Now what this is saying is that if I can find the F that maximizes, that's the solution to the data box, and let U, V, and G be any feasible solution, in other words, they're possible, they may not be the minimum solution, but they're possible solutions, then it turns out that F naught, the biggest maximum that you can obtain, is always less than or equal to the minimum. Okay, so it says for any feasible vector V, the value G equals VB is an upper bound to the maximum value. So if you solve the maximum problem, then that tells you something about the minimum problem. You can't do better than the solution to the minimum problem, to the maximum problem. Now the same thing works the other way. If I have an optimal solution to the minimum problem, and x, y, and f are any feasible solution, so we'll talk a little bit about what more feasible means, then this feasible solution is always going to be less than or equal to the optimal solution for the minimization problem. You can't do any better. You can't do any better. Okay. So what does feasible mean? Feasible just means a solution that satisfies these conditions without necessarily minimizing this value. So you just find v, u, so that these conditions are satisfied, but we don't necessarily get the smallest possible value in this expression when you multiply by b. Same with feasible solution for maximum problem. You get the x and y that satisfy these conditions here, but don't necessarily maximize the function here. Okay, so let's take a quick look at the proof. And the proof, once we've got things set up from the previous observation, things work out very easily. So there are two keys to this proof. The first key is to notice that all the variables that we're using in the problem are positive. They're all positive. The second key to the proof is noticing that this equation holds for any solutions to any feasible solutions to the two dual problems. Right? So I can have, as long as I have u, v, y, and x satisfying the conditions, this is going to be true for g and f. So how do those work together? Well, if I have g minus f equals vy plus ux, and all of these variables are positive, the v, the y, the u, and the x are positive, this number on the right-hand side must be a positive number. In other words, g must be bigger than f. So any g, which is a solution, must be bigger than any f, which is a solution. That means that any g must be bigger than the biggest g, and any f must be smaller than the smallest g. Okay? So those two work together, and that's basically how the theorem works. And I invite you to read through these examples. Well, let's do them together. Okay? All right. All right, this example refers to the tableau in figure 15, so let's go back there. So first we find a feasible solution to the maximization problem. Feasible just means that it satisfies the constraints without necessarily being maximal. So figure 15, the tableau is here. So I need to find x1 and x2 so that 5x1 plus 2x2 minus 180 is a negative number. And also 3x1 plus 3x2 minus 135 is a negative number. I don't have to worry about this because I'm just looking for a solution x1 and x2 that satisfies the two constraint equations. And you can verify that x1 is 10, x2 is 10 works, and the result gives you y1 is 110, y2 is 75. All right. Now if you make this choice, then the value of the profit is going to be 300x1 plus 200x2, which gives you 300 times 10 plus 200 times 10, which is 5,000. Right? So that means right away we can tell that if we read this tableau as a minimization problem, the smallest possible minimum is going to be bigger than 5,000. All right? Now we could go the other way. We could select V1 and V2 to make sure that this result is positive. So we'd have to select V1 and V2 fairly large. And the choice he made is that V1 equals 50, V2 equals 40. And if you set V1 equal 50, V2 equal 40, you can work out that U1 will be whatever. U1 is 70 and U2 is 20. Right? U1 is determined by the equality of this common column equation. So here we have a solution where V's and U's are all positive. And you get the result for VB as 14,400. So the solution to the maximum problem can't possibly be better than 14,400. Okay? And in fact, the optimum value of the maximum problem is 12,000, and later you will show that, well, I'm not sure if we will, but we'll mention that the best maximum problem solution is equal to the best minimum problem solution. Now, if you actually find the very minimum value for the minimization problem, that's going to be equal to the best maximum for the maximization problem. All right? So here's another example you can read through, and I think that's good for us for now.